Okay, so integration by parts actually harkens back to something you've seen before called the product rule. Do you guys remember doing the product rule back in Calc 1? Most of you did it last semester at Dr. Marsh, another university perhaps, or high school. Product rule. So what was the product rule? What did it say? What do you do when you try to take the derivative of a product?
Take the derivative of one function and then multiply it by the original of the other one, and then add it to the derivative of...
The opposite, right? Flipped around, yeah. So we take two derivatives. We take the derivative of each piece, but we don't multiply the derivatives together. That wasn't the product rule. We wish it were. It would be great if it were, but it isn't. It does not work. So I'm going to write it the way that I normally do, simply because it'll follow through to the next portions of their theorem really well. So I tend to rewrite the first piece as it is, and then do the derivative of the second. And then, okay, the stylus has let me down here. And then do the opposite way. And so I'm going to write this a little bit funny just because I want the derivatives written at the back. Okay. So if we took this information and then we did the antiderivative or the integration symbol on each of them, like so. Okay. Well, the first one is an antiderivative of a derivative, so it just becomes u times v, right? Well, the next two are a little different. I have the antiderivative, and another way of writing, for what our purposes are right now, of writing v prime is going to be dv. And then I have an antiderivative, and I've got v du. Okay, so the only thing we've done so far is notation stuff, right? We've just played with a little bit of notation. And the reason we did so is because if we rewrite this formula, we actually have integration by parts formula. And that's what our next information is. So take a look. What we're going to do is I'm going to have the antiderivative of u dv, and it equals uv minus the antiderivative of v du. Write it first, and then I'm going to go back to the last slide so you can see where those pieces came and went from. Pencils are stopped. So if you take a look back at this last slide where I had the formula, all I've really done is I've subtracted this piece to the other side, right? And then I have that formula that I just wrote on the other side of the paper. All right, so you need to see how it works so you can see what the deal is with this, okay? So in general, you need to know a couple of things to be thinking about. When you use integration by parts, in fact, let me look over here. Notice you've got two components over here. You've got u and you've got dv. You have to identify which pieces of your antiderivative are going to be associated and called u, and which pieces are going to be associated and called dv. You have to sort of make specifications. It's like doing a substitution, but you have to pick two parts of it. Pick two places where things are going to go, all right? So there's a couple of things that I'm writing down, and they don't work all the time. They are guidelines at best, okay? At best. The more you pick, the more you're going to be thinking correctly on how you make the choices. But these are some guidelines to help you when you're thinking. You can often let dv be the most complicated thing that you're still able to take an antiderivative of, okay? That's often helpful. That eliminates dv from being some things. For instance, dv cannot be natural log of u, or natural log of x, because you do not have a form on your sheet that tells you what the antiderivative of natural log of x is, right? So dv can't be that. It's just not possible for what we're working with. Now, another idea here is the second one, the u. Often, we would like for things to get simpler. And there are functions that get simpler when you take their derivative, and there are functions that simply just recreate themselves. Okay? They do. Right? Tell me a function that gets simpler when you take its derivative. X squared. Right? It was a quadratic, and you take its derivative, and it becomes a linear, 2x, right? It becomes cleaner or simpler when you take its derivative. Okay, so that's a good thing. So it's often helpful to let u be something that it becomes simpler when you take its derivative. Now, what are some functions that just sort of recreate themselves when you take their derivatives? E to the x does it. What else? There's another one. Sine and cosine. There's the trig functions, yeah? You do sine, and then you get the cosine, and then you get sine back, and then you get cosine. So we can keep going round and round all day, and they don't get any simpler when I take their derivative or their antiderivative, right? They don't clean up any, okay? So, again, this does not always work. Sometimes we actually don't let u be the thing that gets easier. We let that be dv, okay? So I'm going to give you some examples, and we're going to see how we go. All right, so do you see two functions? This is a trick for learning or knowing that you've got u substitution or integration by parts. Both u substitution and integration by parts look like you've got two functions multiplied, and that's what this looks like, right? Yeah. And even if I let u be ln x and I took its derivative, it's not going to equal x cubed, is it? No. So u substitution fails at this. It doesn't have enough substance to it to work. So integration by parts, however, will work nicely. So I'm going to try this. Let me see if I can make my keyboard write better. All right, so what I'm going to do is I want to identify u, and I'm going to find du after I identify u. And I want to find out what is dv going to be and identify v after that. That's not bad. So this whole process starts with me filling in these two pieces of information. I'm filling in the diagonal, okay? So I need to let u be something, and I need to let dv be something, and believe it or not, I don't have a choice here at all. What do you think u has to be?
Natural log of x.
Yes, it has to. Because I can't let natural log of x be the dv because I don't have a closed form for the antiderivative of natural log x. I'm not able to do that. So I want to put the natural log of x here, and the reason I do is because I can take the derivative, i.e. the du, of natural log x. I'm able to do that. That means by default that x cubed has to go over here, and it's x cubed and dx actually, because all of the pieces have to go somewhere. All right, so once we have filled in those two pieces, because that is the formula or the expression we were given, now we actually take our derivatives and antiderivatives. So what is the derivative of ln x? 1 over x. And it's actually 1 over x dx, right? Just like when you do u substitution. Now, over here on the right-hand side, you see the dv. Now, dv is a derivative, so x cubed is a derivative. So if I'm going to go back up, going up a level, I need the antiderivative of that because that's what v is going to be. So what is the antiderivative of x cubed? Good. So in the middle of this problem, we did both a derivative and an antiderivative, didn't we? And that's what happens when we work with integration by parts. Every time we're doing them both at the same spot in the process. We have to do both. Okay, so let's go back to our formula again and see what it's telling me to do. I've identified where things need to be. So I've actually got the left-hand side of this equation, and the right-hand side says what I do is I multiply u times v. Okay, so that's what I'm going to do first. All right, so I multiply u, well, that's ln x, times v, which is x to the fourth, over 4. And then go back to my formula. Then it says I subtract v du, well, the integral of v du. So I subtract an integral of v, which is x to the fourth over 4, times du, which is 1 over x dx. So here's how I remember it. I think visually. I'm a very visual person, okay? So I feel, when I think about this, I know I plug things into this diagonal, okay? And then when I work with my formula, the next thing I do is I multiply across the top, and then I subtract my other diagonal. Okay? So I fill along one diagonal, I multiply the top, and then I subtract the other diagonal. I think I just did my things in the air all wrong. But yeah, so I fill in one diagonal, which would be this one right here. Okay? And then I do the top minus the other diagonal. I think I did the right motions in the air. Okay. And we actually haven't finished the process. We actually have to simplify this and take antiderivatives and whatnot. So I'm going to simplify this. I'm going to put the x to the fourth over 4 in front, simply because I don't want to confuse that and sort of combine that into accidentally with the x that's inside the natural log. So I'm going to write this as 1/4, and I've got x to the fourth ln x. And I can write the 1/4 here in front of this antiderivative as well. And then inside I've got x to the fourth times 1 over x. And what is that? X to the third. So I went from something that I was not able to do an antiderivative of because it looked like multiplication to something that still looked like multiplication, but I was able to simplify it so that it no longer does, right? And I can actually take the antiderivative of that now. So what's the antiderivative of x cubed? Right. So I have all the pieces that I had before. And as Cameron said, this one then is x to the fourth over 4. And what am I missing? Plus c. Now, we didn't have any plus c's in the last chapter because all of our integrals were definite integrals, weren't they? They all started at somewhere, usually 0, and ended somewhere else. And that's fine, but we have to remember now that we're back in this, and you need to remember when you get to your basic skills test on Tuesday, plus c or it's wrong, especially on Tuesday, because if it's wrong, and you got to do it all over again, right? Okay, so I had one student who got every problem wrong last semester because he had a plus c on everything. I didn't even grade it because there was plus c. He missed the plus c off of everything, and so I didn't even grade it. When he came in my office, we actually graded it, and he would have had 100%. He had them all correct, but the plus c's were off on all of them. So yes, I'm going to be mean. Make sure you put a plus c on, okay? All right, I think I'm finished with that one. Well, we'll do one more simplification. We're going to have 1/4 x to the fourth ln x, and then I have minus 1/16, or x to the fourth over 16. Plus c. Is that good? Got the basic idea? Because the next one's more interesting. Okay, so this one right here has the property, if you will, that one of them is a polynomial, it's x cubed. So it will get simpler if I take its derivatives, correct? And it's got a feature of the e to the x. And the e to the x doesn't get simpler or easier no matter how many derivatives or antiderivatives I could take. So it doesn't matter where I put e to the x, because wherever I put it, I can do its antiderivative and its derivative just as easily. So I want to put the x cubed somewhere that makes the problem get easier. Are you tracking with me? Making sense? So when I'm approaching this problem, I want to sort of evaluate in my mind, what kinds of functions am I dealing with? Do they get easier, or do they just reiterate themselves? What's going on with the functions that I'm actually working with? So as I look at this one, interesting things are going to happen. So I need a u, and you have to write out the u and the u. You have to write all this out every time. And if you please just write it in the same places, then I don't have to look for it, and you won't get confused about where things go, because we can all remember visually that we fill in the diagonal that goes top left to bottom right. We fill in the u and we fill in the dv. So what am I going to fill in for u? X cubed. I like x cubed in this spot, generally speaking, anyway, because when I take, like I said, when I take its derivative, it gets easier. That's a 3, pretend. All right. The other spot I fill in is along the diagonal, the dv. So the dv then will be, thank you, and it's actually e to the x dx, right, Hannah? Yeah. Okay, so those are the pieces I fill in from the information that I was given to start with. The other two pieces I get by actually doing some calculus. So what is the derivative of x cubed? Thank you. And it's actually 3x squared dx. And then I go over to the dv, and now I'm thinking backwards. I know it doesn't matter on this one, but you have to start keeping in your mind what you have to think. I need the antiderivative of dv. I need the antiderivative of e to the x, which is e to the x. All right. Okay, so I filled in the one diagonal, top left to bottom right. The next thing I do is I rewrite this. And I rewrite this as u times v, so I multiply across the top. That is x cubed times e to the x. And then I subtract the diagonal that I've written in red. Okay? So this is the integral of 3x squared times e to the x dx. And what do you notice? What's that, Cameron? You have to do it again, don't you? I still have two functions that look like they're multiplied, don't I? I mean, it's not x cubed in e to the x anymore, but it's x squared in e to the x. So I got to do it again. So I'm going to do integration by parts again inside of the same problem. All right, so I'm going to identify. It doesn't become more complicated. It's actually easier than doing u substitution within a problem more than once, because everything really does stay in x's and y, or in x's or whatever variable you're in, it stays there. So I've got u du and v dv. I fill in u and I fill in dv. What will u be? 3x squared. For the same reason, right, Hannah? I want it to get simpler. And will 3x squared get simpler if I take its derivative? Yes, it will. So that makes dv the same as it was last time, which is e to the x dx. Okay, now I get to do calculus. What is the derivative of 3x squared? Please. Somebody saying it? Thank you, Dylan. 6x dx, right? What is the antiderivative of e to the x? E to the x. Okay. Now, I can't lose any of the pieces of the formula that I've already got going on with me, right? Okay, so up here, I still have an x cubed e to the x. Still have that. I still have a minus, right? And the next thing that happens after that is I need another u times v, because I did integration by parts for the next part again. Well, u times v is 3x squared e to the x. Now, I'm going to go ahead and put them in this step because I don't want to confuse you, but I do have a minus next, but it's got a minus on the inside and that minus on the outside. So in a minute here, I'm going to be a plus. But within the formula itself, so this piece right here is coming into play right here only. All right, so I did the top, 3x squared and e to the x. Now I have to do the other diagonal, which is the diagonal I put in red. So that's minus an integral of what? Thank you, Erin. 6x e to the x. dx, because we're still working with our antiderivatives. I'm going to go ahead and distribute the negative through, because if I don't, we're going to get so many negatives and so many parentheses that it's going to be hard to keep track of them, and I don't want us to lose a negative somewhere or keep one that we shouldn't have kept. So this is x cubed e to the x minus 3x squared e to the x plus the integral of 6x e to the x dx. And what do you notice? I got to do it one more time. I still have two functions multiplied, don't I? So I'm going to do integration by parts 3 times within this same problem. Okay, so I need a u, I need a du, I need a v, and I need a dv. What's u going to be? You guys are getting good at this by now, right? 6x, you bet. And dv is going to be what? E to the x dx. We even remember the dx that time. Wonderful. All right, now we can take a derivative and an antiderivative. What is the derivative of 6x? 6 dx. And what is the antiderivative of v? I'm sorry, the antiderivative of dv? It's another e to the x. Okay? All right, so I've run out of space on this slide. I'm going to do one more. So I need to transpose what I have so far. I have x cubed e to the x minus 3x squared e to the x. Is that where I am? Is that all I have at this point? And then a plus sign? And now I need the u times v. So let's cross the top. That would be what? What's uv in this problem at this point? Right. 6x e to the x. Looking good. But I have minus an antiderivative, and this will be of the red diagonal. And my red diagonal multiplied out would be what? Six e to the x, right? Yeah. And we're so close I can almost taste it. So I've got x cubed e to the x minus 3x squared e to the x plus 6x e to the x. And then I need the antiderivative of 6e to the x, which is not a product, right? Because I don't have x in two locations. What is the antiderivative of 6e to the x? 6e to the x. And it's negative because I already had a negative there. What am I missing? Let's see. It's so fun, I can hardly stand it. How about you? You think you've done this before? All right, we're going to do one more, and we'll see how that goes. All right, C. X squared cosine x. It looks similar to the one I just did, doesn't it? But it only has an x squared in it, not an x cubed, which sort of should ring true to thinking maybe I don't have to do quite so many integration by parts in it, so many steps. I've also got a cosine x in here, and what did we talk about cosine x and e to the x kind of being alike? How are they alike? Yeah, when we do their derivatives, just like e to the x, it kind of just goes, it's a cycle, keeps going round and round. Sine and cosine do that too, right? They just go round and around on their derivatives and antiderivatives. So this is going to have the same kind of setup that we did just a moment ago. All right? I'm going to have u equal to what? x squared. And I'm going to have dv equal to what? Cosine x dx. Okay then, what's the derivative of x squared? 2x dx. And what is the antiderivative of cosine?
Sine.
That is sine all by itself, no negatives, right? Right, yep, just sine. Okay, so I'm going to come down here, and I'm going to take this function and rewrite it. So this will be equal to, so we're going to multiply across the top, so I have x squared sine x. Minus the integral, and now I multiply my red diagonal together, which means it's going to look like 2x sine x dx. So far, so good? But I got to do it again. I've still got multiplication here, right? I have two functions, both of which have x's in them, which is what makes them separate functions, having that property of a product, basically, that need to be dealt with. So I've got to identify u, du, v, and dv. What will u be?
2x.
What will dv be? Sine x this time, yeah. Sine x dx, actually. Okay, then, what is du? 2 dx. Oops, wrote the wrong one. What is v?
Negative cosine.
It is negative, yes. Negative cosine x. Okay, so I've still got the x squared sine x in front. I've still got a minus, which I'll distribute in a moment just so I don't lose track of them, because I got a lot of minuses going on, and you're going to see that really quickly here. Now I'm going to multiply u times v, and what is u times v going to be?
Negative 2x.
And then I need minus an integral. I have to do the other diagonal. So I've got another negative there, and I've got a 2. So this is negative 2 cosine of x dx. And do you see all the negatives in this problem? You have a lot of them, so be careful when you're working with the negatives. It's so easy to lose track of them. So I'm going to work on cleaning those negatives up next. So I've got x squared sine x here, and then I've got this negative and this negative, so this is positive 2x cosine x. And then I've actually got 3 negatives, don't I? One on the outside, one in front of the integral, and one inside of the integral. So 3 negatives means I'm going to still be negative. So this is actually negative the integral of 2 cosine of x dx. And give me just a second and I'll copy this to the next slide. All right, so the first piece stays the same, and so does the second. And then I have minus what? What is the antiderivative of 2 cosine x?
2 sine x.
Yeah. And then what? Let's see. I'm trying to get a dot above my eye. Okay, there we go. And then we're finished. Now, lest you think that this whole section, if you do plan to go ahead and start this section, I want to show you this problem without doing it. We'll finish this problem next time. We're going to do some board work before you leave, okay, some practice on antiderivatives. But let me show you this problem real quick. This section is about integration by parts, but every bit as much about identifying when you need integration by parts as identifying when you do not need it. All right, so there are a few problems. This is one of them, or an example of one of them, where integration by parts is not needed in this particular problem, okay? So we'll finish this problem last time, but be on the lookout if you do decide to go ahead and start, because it is the weekend. It would be great if you could actually start this section. It would be awesome, so you don't end up with 2 sections between Tuesday and Wednesday next week, because otherwise you're going to. But this section right here wants you to also be able to look at and identify when it's not necessary, because you do not need it on this particular problem, okay?